Hello everyone, welcome again to our series webinar for PESDAY 2023. This webinar is a series for PS Day, and I think this is the last one for this year. Another next webinar is about a workshop for IEEE PES young professional, and hope this is not the end of the PS Day webinars. Next we will be welcoming our Dr. Ahsan Razzaqullah, is a PhD and senior member of IEEE. He will give us a valuable webinar about power to green hydrogen, a step toward net zero emission. So let's welcome him. Welcome, Doctor.
Thank you very much. Thank you, Mr. Saif. And thanks for inviting me for this webinar today. And I really appreciate this effort. And thanks to IEEE Iraq section for taking initiative on this webinar. And of course, IEEE and IEEE PES Society. So as you already mentioned, that's power to green hydrogen. Basically, in this webinar, I will try to give you an overview on global hydrogen demand and its status, its classification, which is basically coming from different types of sources. Based on sources, the names are basically given. Green hydrogen production process, role of green hydrogen in net zero emission. What is net zero? How green hydrogen can help in achieving net zero emission target by 2050. And hydrogen for large-scale energy storage, I will slightly touch upon it. Mostly, I will spend a bit more time on a framework for techno-economic and environmental analysis for wind to green hydrogen production plants, where basically the models of sizing different subsystems are shown. Is basically in the paper. I didn't put the models here because there are a lot of slides and equations. It will not be matching with the time, so I just show the results and so on. But the papers is there. People can go and check the models and the whole framework. So it will also outline the future prospects and challenges of green hydrogen deployment and development. So let's look at the demand and production globally. So basically, it's not new that the people are using hydrogen. It's since been a long time people are using it as a fuel and as a raw material for both chemical and metallic industries. However, the fact is that these cannot be obtained in its pure form from nature. We have to have manufacture it or produce it. It has to go through a process to get this hydrogen. So if we look at the broad spectrum of hydrogen applications, so the hydrogen demand you can see in all around all sectors. For example, transportation sector, heat and power applications for building, heat and power for industry feedstock, mobility, and others applications. I will not go through these. It's basically just to highlight or to show you that how the hydrogen demand can be increased considering its massive applications around us. So if you look at the hydrogen demand, it is in million metric ton. By 2018, it's almost 38 million metric ton for refining purpose, 31 million metric ton for ammonia, and some other applications is 4 million metric ton. So if we look at the country-wise, the consumption according to the country-wise, so it's basically, you will see that the North America and Northeast Asia is basically the highest highest amount of consumption happens in Northeast Asia, then North America and the rest of the world, where basically Middle East is part of it, and Indian subcontinent and Western Europe. So it's basically everywhere you can find the hydrogen consumption. However, this picture will change maybe in few years' time, considering the application and the possibility of generating clean hydrogen. As you can see here, in 2020, China was the top list of country that consumed hydrogen, around 23.9 million metric ton. US came second place, and followed by India, which is 7.2 million metric ton. It has been shown that 4% of hydrogen production comes from electrolysis process, 47% comes from natural gas, 27% from coal, and 22% from oil. So you can easily see the highest, the most of the hydrogen production is coming from the fossil fuel. By 2021, only 1% of global hydrogen comes from renewable energy, so which is just nothing, or we can say it's just starting of green hydrogen journey. By 2050, China will demand 24% of global hydrogen demand, 25%, and India will be following it, but because India will increase its steel production by 4 times using the hydrogen. So you can see that there's a big demand coming. United States may hold the 3rd place because of increasable pace in transportation, because you all know that electric vehicle is coming, and the vehicle with fuel cell that is basically based on hydrogen is coming. So it will have a big impact in those countries as well. So if we look at the hydrogen storage, normally there are 3 technologies: use the compression or the liquefaction. 3 stages, 3 ways. Right now we have the market, and the other one is the material based. And if we look at the country-wise, the hydrogen energy storage market is basically Asia Pacific is the biggest market. Then you have South America, Europe, Latin America, and Middle East. So if we look at the global hydrogen demand and production, the comparison between the production methods and its prices. So let's say these are the source of hydrogen production. Electrolysis is cost about $2.5 to $3.5 per kilogram, and natural gas without CCUS, you probably already know CCUS is the carbon capture, utilization, and storage. In short form is CCUS technology. Without technology, this means this natural gas-based hydrogen produce a lot of carbon dioxide emission, and its production cost is 0.5 to 1.7. Natural gas with CCUS, which is basically carbon capture, utilization, and storage, that's basically cost 1.5 to 3.7. Coal without CCS technology is 0.9, is quite cheap. Coal with CCS is 1.44 and to $2.11 per kilogram in China. While the renewable energy cost for per kg hydrogen production is $3 to $8, depending upon the technology and the location where basically the hydrogen production happening. In other words, the renewable energy is producing, because you know that renewable energy is based on the site. So if you have a good site, good resources, you have the higher capacity factor for the renewable sources, so that you can produce more energy, so that the cost can be reduced. However, if we consider the cost is still higher end for the renewable energy, which is considered to be a green hydrogen. So you can easily see this: most of the hydrogen is coming from the natural gas or maybe coal-based, means fossil fuel. And although cost is low, but it produces significant amount of carbon emission. So if we look at the hydrogen classification, so it's basically, I can say it's a source-driven hydrogen classification. Why? You will see in a minute. Because first one, if I say gray hydrogen is basically coming from natural gas, and it's producing through steam reforming process. So this is least expensive and most popular type of hydrogen production. And source of hydrogen production is natural gas. However, this produces greenhouse gases. We all know that, because this has no even other technology in it, like CCQ. If you don't use it, of course, all of the carbon dioxide that will produce will emit to the air. So the second one is called blue hydrogen. In blue hydrogen, is also can be called as a low carbon hydrogen, because in this case, although the source is natural gas, but steam reforming happening with carbon capture. So in this case, whatever carbon is coming out of the production process, that will be captured and stored However, in case of gray hydrogen, it was just emitted to the air. So that's why the blue hydrogen is now getting popular also, and it can be considered as a low carbon hydrogen. But it's not completely. I mean, the carbon dioxide cannot be completely eliminated from here. Or even though you try to capture it, there are some leakages might happen. So there will be some carbon dioxide emission happen in this hydrogen production process. Black and brown hydrogen, this coming from the source is coal, basically it's coming coal-based, and process is gasification. And of course, this is probably one of the worst that will produce most of the carbon dioxide. Here, this coal material basically converts as a carbon, such as coal and hydrogen and carbon dioxide. So this happened through the gasification process. It is very harmful, most harmful type because of emissions that cause air pollution. The one that is coming from the nuclear energy source based, and it's following the same procedure like electrolysis process. It's also called pink or purple or red hydrogen. It's basically the major energy here is basically coming from nuclear energy. And you all know that the nuclear energy is not not every country has the capacity to develop or to operate this type of energy resources that limit this type of hydrogen production as well. Turquoise type hydrogen, this is a kind of new also. It's also called low carbon hydrogen. So in this case, basically, source is natural gas, again is fossil fuel, and pyrolysis process is used here. In this case, so basically, is produce solid carbon and hydrogen, and during this process the materials that makes up a chemical makeup is fractured using the heat. They use the heat in this case and creates solid carbon that does not emit any gaseous carbon. So the difference here is the carbon that is produced is solid, so it's not gaseous that it will dissolve with the air. So this is one of the good things. That's why they said that it's a low carbon, and it has also popularity, and it has some future. However, the one that we are basically targeting and we are interested for is the green hydrogen, and that is coming from the renewable sources, and it is done through the electrolysis process, either water electrolysis or solid oxide to water electrolysis. There are different types of technologies that can be explored. The very common one is alkaline type water electrolysis. So here, mostly the energy that needed by the electrolyzer that is coming from the renewable source, either wind or solar or any other type of renewable sources. So these are the different types of hydrogen, but mostly in the market you will find the gray hydrogen or the blue hydrogen, and renewable hydrogen is, I mean, the green hydrogen, which is coming from the renewable, is the future that can have no emission at all. So green hydrogen production process. So if we look at the green hydrogen, now if you probably notice that we are narrowing down to the green hydrogen. I'll be only talking on this electrolysis process using the renewable sources. I will briefly touch on two process. So water electrolysis is one of the process. In this case, you have renewable energy that is coming from the photovoltaic panels, or maybe wind turbines, or probably hydropower, or this power can be considered as an input to the water electrolysis system. These water electrolysis, there are 4 technologies can be used. As I mentioned, the solid oxide water electrolysis, alkaline-based water electrolysis. There is proton exchange PEM, which is proton exchange membrane water electrolysis. The other one is anion exchange membrane water electrolysis. So out of these 4, basically the most popular one is PEM type. Alkaline is low cost, but it has some other limitations. But the water electrolysis, which is using PEM, proton exchange membrane, is the most popular one. The other 2 is solid oxide and the ion exchange membrane. It's actually still in the development stage. And then this produced hydrogen will be storage for green hydrogen. The hydrogen produced in this case can be stored, or we can convert it for the electrical energy if needed using fuel cell, or we can use this hydrogen for transportation to send to the load center, especially where the needed, or we can store it for further use. So as I said, the water electrolysis process, basically the energy come from the renewable sources, which is solar and wind or some other sources, geothermal and so on. These basically will passing to the input to the alkaline water electrolysis system. So that produces the hydrogen and oxygen. By the way, hydrogen is useful that we understand. Oxygen that is coming from here is also a good product, byproduct. So basically, this oxygen can be even stored and can be used for purposes there where we need the oxygen. So it has 100% benefit. We can capture both hydrogen and both oxygen here. Biomass or biomass gasification or pyrogasification. So this is another process of producing green hydrogen. So this gasification is not a new technology, but it can be explored and it can be looked into the techno-economic analysis and its feasibility analysis for the countries where these type of sources are available, because it's basically used sorry. I'm sorry. What happened? So it's basically used is as I said, biomass or pyrogasification is basically an old technology. However, it depends on the country because it needs the resource or sources like wood, biomass, crop residue, non-recyclable plastic, old tires, and others. So basically, it's coming from the waste. If you have the waste and enough waste, so you can use that as a feedstock, and this waste is basically heats up at a very high temperature, which is 900 degrees to 1200 degrees Celsius, in the presence of a small amount of oxygen. So from there, you can get the, you do the gasification, and then this you can get complex gas containing hydrogen from organic matters. That is, we are talking about like wood, biomass, crops, and residue. So basically, this is another process that can be used for green hydrogen production. However, for green hydrogen production, I think wind and solar is more convenient. The technology is more matured, and it can be more much more better than probably this gasification process and so on. So now, how this green hydrogen can be a catalyst to reach to the net zero emission. So what is basically net zero? Net zero emission basically refers to achieving an overall balance between greenhouse gas emissions produced and greenhouse gas emission taken. Net zero doesn't mean that the emission will be zero. No, the emission will be balanced, which is basically the amount of greenhouse gas emission you produced. At the same time, the same amount of greenhouse gas emission it should be taking out from the atmosphere. So let's say as long as they are balanced or equal, we can say net zero emission. So this net zero emission is target to achieve by 2050. Many countries are targeting, so we'll see that. So net zero doesn't mean that the emission will be zero. It's just a balance between whatever is emitting and whatever greenhouse gas emission can be taken out from the atmosphere. As you can see here, the renewable energy can be used for electricity production. This electricity will pass to the electrolyzer process or electrolyzer system that will produce hydrogen. This green hydrogen can be distributed and used for different application. You can use in industry, you can use in home application, you can use for transportation. So that is the way to reach to the net zero emission as predicted. A bit more on it. So this is basically a roadmap to reach to a net zero emission. It is expected that by 2021, which is already passed, that no new unabated coal plants, it is supposed to be no more coal plants should be approved for development. Okay, so 2025, no new cells of fossil fuels boilers. So one of the components, which is boiler, by 2025, it is that they will stop the selling this type of equipment. So by 2030, there are number of initiatives. That's universal energy access. All new buildings are zero carbon ready. So any new buildings will be equipped with zero carbon ready. 60% global car sales are expected to be electric. Most new clean technologies in heavy industry demonstrated at scale. and there's some target to produce solar and wind addition and so on. So and by 2030, it is also expected 150 million ton low carbon hydrogen should be produced, and 850 gigawatt electrolyzers should be deployed. So by 2035, again, there are some other milestone. In it's expected 4 gigaton carbon dioxide captured. By 2040, 50% of existing building retrofitted to zero carbon ready levels. 50% of fuels used in aviation and low emissions. So you can see there are a lot of initiatives are taken, and if it goes as planned, so it's basically by 2050 you will see the contribution of carbon dioxide or greenhouse gas emission will be much lower compared to 2020. Here in 2020, if you look at the majority contribution of the greenhouse gas is coming from electricity and heating. Then next one is the industry. Then you have the building. This one is building, and rest of the other. So basically, this is the contribution of greenhouse gas emission in 2021, and this is expected to be 2050. Sorry. So in 2050, what is expected? More than 85% of buildings are zero carbon ready, should be. More than 90% of heavy industry production should be low emissions, and almost 70% of electricity generation should be globally coming from solar and wind. So this is the target. So if it goes through this, go smoothly for this target, so then it's easy to achieve zero emission. But we don't know. There are some lot of uncertainties. There are a lot of predictions here, so we have to wait and see. If you look at the greenhouse, the net zero emission target by the countries, some of the leading countries, they are thinking to achieve their net zero emission by this. For example, Iceland, United States, by 2050. Most of them has 2050 here. Some leading countries, not all listed here, and China by 2060. So they are targeted to achieve net zero emission. So what to do to achieve this net zero is basically we need this kind of holistic and multidisciplinary involvement in clean energy innovation. Requires further rapid deployment of available technologies. Innovation opportunities should be looking into for advanced batteries, hydrogen electrolyzer, and capture and storage. Hydrogen electrolyzer, basically the more efficient technology we need. Clean energy innovation must be accelerated with the understanding or with the government incentives and R&D, and also demonstration and deployment at the core of energy and climate policy. So basically, it needs the cooperation from all the way, researcher, policymakers, government, and all this. So wind to hydrogen production, I will talk about this techno-economic assessment. Actually, this paper is published in Renewable Energy in 2022. This is wind to hydrogen production, and this framework is developed considering a case study in Sultanate of Oman. And I'll give you a brief overview of what Sultanate of Oman is doing on this hydrogen production, or their net zero target. Hydrogen is mainly coming from natural gas in Sultanate of Oman, and it is expected to grow hydrogen fuel cell vehicle deployment here. So the country is really looking into the hydrogen fuel cell vehicle deployment, and country is expecting to produce 1 million tons of green hydrogen by 2030, or in 2030. Sorry. So this is one of the country's vision or plan. Having no carbon emission in 2050. So by 2050, they are also trying to achieve the net zero emission. As a result, they have some target to include almost 40% of renewable energy. 40% of their consumption should come from renewable by 2035. So that's one of the ambition they have. Also, with this, they have planned, starting 2028, they have planned to construct a green hydrogen plant, which is 25 gigawatt solar and wind resources in one of the governorate in Oman. And the full capacity will be taking place in operation by 2038. And this is probably would be one of the biggest in the Middle East region. And the project will run in few stages. Other than there are five other agreements also been signed with the company Hydrom. It's happening especially in the areas like Duqm. Duqm has a big port here, many of you might know, and the company here is BP Alternative Energy Investment Limited. They are given this much of areas, and 3.3 gigawatt power plant should be constructed for hydrogen production. Governorate of Dhofar they have, Salala, Dukum, there is undefined places also. So there are five other projects also going on in terms of developing hydrogen plant in Sultanate. The framework that is actually I'll be talking is starting. And first of all, since it's a wind-based hydrogen production, I mean green hydrogen production, we need to look at the location or the site selection. So number of sites were selected here, and weather data were collected, and cost data for the different components of technologies been collected. And then wind turbine selection based on the wind turbine, because you want to select a wind turbine that can turn on with the lower wind speed, or I mean the low cut-in wind speed, so that you can go to the production immediately. Because in Sultanate of Oman, wind is not that great compared to solar in country, or maybe compared to the wind in other locations. So we need to be careful in selecting the wind turbine here. So then we use this data. The first thing that we need to look at the air density correction for this wind turbine, because wind turbine normally you know that it's operate at a higher elevation with a hub height, and the air density at the hub height is not same as the air density standard temperature and pressure, which is given for the which is basically used to give the power curve for the manufacturer. So the manufacturer they give us the power curve that is basically based on the standard temperature and pressure, which is basically the air density, which is 1.225. Everybody knows that. However, we cannot use that. To use a particular location, we need to know the air density for that. So that's why the air density correction is required. These equations, although I mentioned here 2 to 7, these equations are available in the reference that I just mentioned before this section of my talk. So then we evaluate annual energy production of wind turbine. This is without considering the degradation of the wind turbine. So basically, we need to look at the wind turbine energy production considering the turbine degradation factor. Turbine degradation factor is basically its performance degradation over the time because of aging, because of weather, and so on. So we need to look at the energy production over its lifetime. So once we know this energy production, we can easily calculate the capacity factor of the wind turbine for the selected sites. And we can also then immediately find out how much carbon dioxide emission can be reduced because of using this wind generation system. And then we can calculate the levelized cost of energy. These information are basically input to the green hydrogen production process. So basically, we can calculate how much the green hydrogen production can happen for a given wind turbine for these locations while we are going through this process. Once we know the green hydrogen production, we can easily calculate the levelized cost of green hydrogen. So in this case, we need an important information, which is called the capacity of electrolyzer, because the capacity of the electrolyzer ultimately is an important factor which will take the energy produced by the wind generator and will give you the output as an hydrogen. So this sizing of this electrolyzer is an important factor in this whole framework process. So after that, we need to do the sensitivity analysis to see or to identify some critical variables that basically has influence on the hydrogen production cost. After applying this framework, so the results that I have found that I will show you here. For example, I selected 18 sites. In 18 sites, basically, the data available, the meteorological data are available. This is the wind speed at 10-meter height, and this is the surface roughness, average temperature, longitude, and latitude. By screening the initial data, we found that some of the site has very low wind speed. So that is basically doesn't fall with any other class, any classes of the wind turbine. So basically, we identified that these sites are not suitable for installing wind turbine. So what we did, we just exclude them and we select 8 sites, which is listed here. These 8 sites: Kevin Herity, Thamrait, Masira, Dukum, Rasalhat, Sur, Sunana, and Karanalam. So these 8 sites has a good wind speed at 10-meter height. Then we extrapolate this wind speed to the 80-meter height, considering the turbine that I selected here, Siemens 113 SWT 113, 3.2 megawatt capacity, and cut-in speed, as I said before, cut-in speed is quite low, 2.5 meter per second, whereas cut-out speed is 22 meter per second. In Oman, especially, the wind speed hardly reaches to 22 meter per second, maybe few hours in a year. So this is the rated wind speed, and half height is 80 meters. So basically, we plan to operate the wind turbine at 80-meter height, considering a lifetime 25 years. And this is the cut-in wind speed, means the wind speed above which the turbine will start to produce power. Now, what we did, if you remember this framework, we first need to do the adjustment in the air density. So this is the standard air density. This is 1.225, 1.225 for all location. This is because the power curve that we got, that is based on this. So now to adjust this based on the site temperature and pressure, we use the model and we adjust this air density. These adjusted air densities are like this: 1.118, 1.17, and so on. So as a result, we got the capacity factor after adjustment of the power curve or the air density, and this is the capacity factor at a standard temperature and pressure. You can see that at a standard temperature and pressure means if you do not correct the power curve or the standard or the air density, then it shows the capacity factor is higher, which is basically you are overestimating. So that's why it is important to consider this. If you look at the energy produced, this is the adjusted power curve, the energy produced by the wind turbine after adjusting, which is 9,395 megawatt hour. While if you do not adjust it, you see the energy could be estimated 9,710, which is almost 3.35% over estimation. So that's why it is important to adjust the air density that we have done. So this process is applied to all other sites, and you can see this the data here. Now, after that, we found this is the energy produced. This is the adjusted power curve, means considering the pressure and temperature from the sites, that gives us adjusted air density, which is basically makes the power curve adjusted, the power curve that we got from the manufacturer. Now, if we consider the degradation factor, we consider degradation factor D equals to 0.01, which is basically 1%, 2%, 3%, and so on. Considering 1% degradation at the end of the 25 years, so the energy production could be 8,280 megawatt hour, while at the first year it was 9,395. So basically the energy difference here is 11.85%, is more or less same for all sites. So basically you can see if we do not consider the degradation factor, we are still again overestimating the energy production. If we do overestimation of the energy, what's the problem? If we do overestimation, then of course the cost of energy that we will get, it will be lower, and that will not be accurate and at the end the payback period and all this will be impacted. So we found the levelized cost of energy for both cases, without performance reduction, with performance reduction. Without performance reduction means we didn't consider the air density correction, we didn't consider the degradation. The other one is considered both. So in this case, you can see the levelized cost of energy is the lowest in the Masira Island, which is almost 0.037, 0.0335, I think 334, and this one is the same site but with performance reduction. So basically, we can see the performance reduction. Considering the performance reduction, you have the higher cost, which reflects more realistic compared to the if you do not consider the performance reduction. So we basically look at then how much carbon dioxide emission it can neutralize or it can reduce. So basically we look at how much energy is produced, and we consider two cases of considering the emission. Case one is basically emission equivalent to natural gas. Second one is emission is equivalent to I think this is natural gas, and the other one is the oil based. So basically based on two different systems, you have the different emissions. So this is the amount of carbon dioxide emission can be reduced. If we have only a 3.25 megawatt, 3.2 megawatt wind turbine, this much of carbon dioxide emission can be reduced depending upon you are considering a natural gas based generation or oil based. In Oman, mostly natural gas based, so we can expect this much of ton carbon dioxide emission reduction per year. So now when we are talking about 25 gigawatt the renewable power generation, you can imagine how much carbon dioxide emission can be taken out from the year. So it will be a great impact on net zero emission. So based on our analysis, we had seen how much the hydrogen production will be happening in each site. These 8 sites, you can see the highest amount of hydrogen production is happening in Masira Island. This is the annual energy production in kilogram, and this is in another unit, which is normal cubic meter. So it's very frequent, or frequently you will find in the literature that they always consider annual hydrogen production in terms of kg. So that's why both units are considered here. So based on hydrogen production, we rank the sites. If you look at, there are 8 sites. We ranked, the first rank was Masira, second was Thamrait, Karen Halitim, Alam, and 6th is the Duqm. Here, one of the things you can see that Karen Hariti has the higher wind speed, however, Masira has the lower wind speed. Although it has lower wind speed, but it is actually producing more green hydrogen compared to the Karen Hariti. The reason is that the Masira has more consistent wind compared to Karen Hariti. The other thing is that Masira is ranked 1, however, Duqm is ranked 6. Although Duqm is ranked 6, but Duqm has more potential compared to this Masira if we consider the transportation of the hydrogen transportation, storage, and in the Masira is an island which has no port, and the transportation will basically add more cost. But Duqm, it has a lot of space, the port is there, it's a kind of economic zone, so it will have the production and consumption in place. So basically, in that case, Duqm could be another good choice, or investor might choose Duqm. So basically, this part of analysis means considering the transportation, the cost, considering for transportation, storage, and so on, the economic evaluation is not done. So this is a limitation of this work. So this is a good area to still explore, which is basically part of the supply chain. The levelized cost of hydrogen, as you can see, this Masira has the lowest hydrogen cost, 3.37, and the others, the highest one is 6.13. So basically, the range is 3 to 6, as you had seen before. While I was presenting earlier, the cost comparison, it's the renewable energy-based green hydrogen cost, production cost is basically 3 to 8, depending upon the location. In Oman, has from 3 to 5.78 with the technology cost that was considered in 2022 and before. But of course, the cost, if you consider now, maybe it will be reduced because of the technology cost reduction and so on. So the degradation factor. So now in this case, we also look at the hydrogen production if we consider the degradation factor, turbine degradation factor. In this case, we consider only Masira Island because we found Masira is the best location here. So in this case, we just consider for that location how much the hydrogen production was. It was 247 ton per year without any degradation factor in the turbine. So it is constant for 25 years. However, if we consider 1% degradation, you see the hydrogen production is gradually decreasing over the 25 years. And if you have 2%, it's increasing even more, and 3% even is more. So turbine degradation factor has an impact on hydrogen production, has an impact on the the carbon dioxide emission as well. So last we did sensitivity analysis. In this case, you can see the cost of the utilization factor, cost of capital, capital cost, which is cost of the technologies, and electricity cost. If we see, we take here base case is basically the material cost, which is 3.37 USD per kg. So in this case, if you look at the electricity cost, it has the highest, the more influence in terms of achieving the green hydrogen production cost lower. So if you want to get the lower cost of the green hydrogen production, electricity cost has to be reduced. What does electricity cost come from? This electricity cost depends on the renewable technologies. So the further the renewable energy technology cost reduction will reduce the cost of the hydrogen production, as well as the utilization factor is important. So higher the utilization factor, you can reduce the cost. So these utilization factor basically depend on the size of the electrolyzer. So that's why the size of the electrolyzer is an important aspect in this type of techno-economic analysis, or the design of a system that can produce green hydrogen. Further, for 20 years lifetime, we consider that there will be a 3% reduction in electrolyzer cost and 4% reduction in electricity cost every year. If we consider this reduction, individually, reduction in electrolyzer cost will reduce the cost maybe from 3.37 to 3 USD per kg, and itself the electricity cost can reduce up to 2, from 3 to 2. But if you consider both cost reduction, it can go up to 1.82 USD per kg of hydrogen production. Of course, this value has to be looking into the cost. It will completely depend on the cost in future. But it's expected that the cost will reduce, so we expect the green hydrogen production cost will also reduce. So what are the challenges? There are some of the challenges I already discussed, which has been put in here. So basically, the electrical energy cost and the capital cost of electrolyzer are the major influential parameters here. So these costs are depending on the cost of the renewable energy technologies and the cost of electrolyzer. We know the massive research is going on in electrolyzer. There are new electrolyzer system which is still under development. If those comes with higher efficiency and with their limitation to be rectified, then we can even get lower cost of hydrogen. For further reduction in the cost, it requires also government incentives and funding. We need to identify suitable sources and sites to develop green hydrogen production, because green hydrogen production is also require a lot of water. This is another issue. So the country or site that are basically having a hard time to get the clean water or even seawater, so for them this type of project may not be very suitable. So in Oman, yes, they have issue in the clean water or drinking water, but they are planning to use the seawater. So optimal design for green hydrogen production plant is critical to optimize cost of green hydrogen. So there are a lot of things can be done through optimization. By the way, the framework that is developed here and presented is not done through optimization. It's just numerical analysis. So there is a lot of room to do the optimization here. So large scale storage. When I'm talking about large scale storage, is storage basically as for producing electrical energy back from green hydrogen. So we can store green hydrogen. We can use this hydrogen using fuel cell to produce electricity, because the grid, utility grid is evolving towards more integration of renewable energy. More integration of renewable energy can put burden on the network in terms of its stability and so on. So in this case, we need a large scale storage. Right now, the solution is battery, but green hydrogen based large scale storage can be a good solution. And hydrogen transportation requires liquefaction, which is energy intensive. This is one issue. Alternatively, also we have hydrogen conversion into other carriers like ammonia, methanol, and organic liquid, it also has low efficiency, means there are significant losses can be produced. Therefore, efficient supply chain system to be developed for green hydrogen transportation. This is another big area that can be people can be explored, especially the industrial engineering people. So what is takeaway from here is I try to give you an overview so that the recognition come on hydrogen demand and applications and its roadmap to achieving net zero by 2050. It gives you that's how renewable energy is significant in terms of producing green hydrogen production. So the deployment of renewable sources is essential in this case. It's also familiar you with the initiatives and activities in order to deploy green hydrogen plant development around the world, explain source-driven hydrogen classification. I hope it gives you clear idea that's what are the different hydrogen are available and so on. It allows to identify subsystems of renewables to hydrogen production for decarbonization future. You probably got to get some knowledge on a framework that performs techno-economic and environmental assessment of wind to hydrogen production. Also, it allows you to see the barriers and opportunities of deploying green hydrogen production. This is some of the references I highlighted here. There are more than this. So that's all I want to end up with this. If you have any question and comments, we can discuss. Thank you all.
Thank you, dear Dr. Hassan. It's very benefit lecture, and you have get all of the information about it. Green hydrogen. It's a very uh, informative lecture.
Thank you.
Uh,
Thank you.
just I have one question.
Mhm.
It's like that. Every time we're talking about technology on something hot topic now, they will be must be related to AI. So how are AI dealing with this topic?
I mean, the AI can be used in these cases. In if you want to make a complex model, we were
Mm,
just talking about one person. Now,
yes.
hydrogen, green hydrogen, can be part of a big system. For example, as I give an example, this hydrogen production plant can give you hydrogen that you can use for pure hydrogen application or transportation or delivering to the loads, which is purely hydrogen load. Also, at the same time, these green hydrogen can be used by using first fuel cell to produce electricity, push this electricity to the grid. Now, this
Yes.
when it comes to this whole system coming to the different players, now how do you get the energy management? In
Yes.
that case, AI can help you to get all the information from every parties, can develop a good energy management system, can rescheduling, can predict the load demand, and can make a schedule. So in that case, the AI would be a very good topic to add into this. Yeah,
Okay, doctor. Uh, I have another question is related
sure.
to my field. What
Mhm.
about sensor technology? Is playing a role part in hydrogen production and green hydrogen?
Of course, sensor probably is I didn't put it here, but and of course probably I don't work in that area anymore. But when you look at the sensor, because it's a hydrogen plant, if you think about hydrogen to transport through the pipeline, okay,
Yes.
you have
Yes.
valve, you have pressure, you have to maintain all this. So how do you get this all this value to your let's say if you want to have an AI system, how you get this all information? It comes through this different sensor. Nowadays you can have even a wireless sensor. So of course sensor will play a big role in terms of controlling its transportation from place to place, and especially if you want to use the existing pipeline. Yeah, that's great things actually reminded me. Yeah.
So every technology come out new, they need some auxiliary things to
Yes,
provide
yes, yes,
there for
yes.
optimal.
Of
Yes,
course, yeah,
something like this.
yeah, yeah.
Let's see if we have any another question. Well, they asking about the role of policies regulation about the green hydrogen, or how to support to net to zero goals. I think it's very important.
Yes, is very important, and I touch upon it. And as I said, this government needs to put forward their hand. Government should be giving some incentives. Government should talk to the players, I mean the companies and so on, because when you want to develop a policy here, also we don't have practical experience to get some experience in terms of developing policy. I mean,
Yes,
you need to have some sort of pilot program, pilot plant. From that plant you learn and you do the policy. And right now it's probably in a white paper policy you can do, and based on that only you can do what you can do. You can learn from some others which are been doing. Based on that, government should come to forwards here. And of course the academia and researchers, they are always ready to support that in developing the policy and so on. So I would say in a country, the policymaker or the governments in the country need to put their hand first with the academia and the researcher in the country, with the global leaders. So all needs here, and of course the societies, different societies are also working, like IEEE and similar other societies. They're also working. So it's a basically a big group work required to develop some sort of policy. So it's always a difficult task, or it's not easy to come up with something. So that's why it's one of the reasons that the any target they take, it takes a bit time towards the implementation, because there is no policy, there is no framework how to
yes.
deploy this. It comes sooner or later. It will come, this is the things. But the initiative should be coming from the country they want. They should have their own target. They should first set the target. For example, I would say in Oman, they are targeting this much of energy should come from renewable. This is their plan to have the hydrogen hub in here. So they are talking to the investor. The investors are coming. So now they have a kind of good guidelines. That's what they are going to do. So this is what we need. It's needed cooperation from all sides.
So, Doctor, do you think is after getting policies and regulation, we need to construct a standard for that
Sure,
or
of course,
guideline?
guideline,
So
because
there is anyone have take responsibility of this, or just this is in general for industry type only?
well, if nobody comes forward, then of course industry will come forward first, because industry will
Yes,
see their benefit, right?
yes,
So
exactly.
industry will see their benefit. They will always look at from the commercial point of view. And already you can see in my presentation that there are a lot of companies already investing here, Hydrom, and there are a lot of Korean companies here, and other companies are already investing. So they will come up with some guidelines. So in this case, I would say that the societies, the bodies like IEEE and other, they should come forward and start to take initiatives to develop some guidance. It's not going to happen in 1 day, 2 day, or 1 year, two
Of
years. It
course.
will take over the time, but of course, it's need an initiative from this side, so that we can involve the other parties to get some standard on that. Yeah.
Okay, Dr. Hassan, we have reached our end for this webinar. I hope you all the best on the next steps, and we can make another webinar next time. Thank
Inshallah.
you,
Thank you
everyone,
very
who
much.
have been with us,
Thank you.
and please be ready for another webinar for workshop, practical things next week, inshallah. Thank
All
you,
right.
Doctor.
All right,
Thank
thank
you.
you very much. Thanks for all audience, and a special thanks to you for arranging and inviting me, and of course IEEE Iraq section and so on. So wish you all the
And
best, and we'll be in touch. Thank you. Bye bye.
thank you very much. Goodbye.
Bye.
Goodbye.